Next we will talk about the induced torque in the induction machine. So what was the expression for induced torque that we have seen? T induced is equal to the converted power divided by the speed, angular speed. Okay. What about the load torque? The actual output load torque that is available, this is equal to the actual output that is available divided by omega m, where the output power is equal to the converted power minus the rotational losses. Okay. So we are discussing about the induced torque here. Now this you can express as T induced is equal to converted power is equal to 1 minus S times the air gap power divided by omega m you can express in terms of the synchronous speed as 1 minus S times omega S. Okay. So this is how you are going to get the induced torque is equal to the air gap power divided by the synchronous speed. So this is an expression that is often used, more often used as compared to this, because the synchronous speed is independent of the load changes. It is constant for a particular machine. Okay, 120 F by P. It will not change. So if we know the air gap power, then we can find out the induced torque. So this expression is more often used. Now how can we express the air gap power? Pg we know this is equal to the power that is dissipated in the R2 dash by S resistance. So that means this was the, we will take the approximate equivalent circuit. Here we have R2 dash by S, this is Jx2 dash, okay, and the air gap power is the power that is dissipated in this resistor, and since this is per phase circuit, 3 times that value. Okay, so that means 3 I2 dash whole square R2 dash by S. This is the current I2 dash here. This voltage that you have here is the V1 voltage you can take. This is the per phase voltage. Okay. So now I2 dash, how you can find out with respect to V1. So because I2 dash will vary with the load, and V1 is the supply voltage, which is the constant voltage that we give. So we would want to express this I2 dash in terms of a constant. Okay. So we can use the Thevenin's theorem here. This entire part of the circuit, if we can replace by the Thevenin's equivalent. Okay. So then what will that be? VTH and ZTH. We will have a resistance and a reactance part. And here you have R2 dash by S and Jx2 dash. This is going to be I2 dash. So what will be the value of this VTH here? VTH will simply be, if you take this as Z1, R1 plus Jx1, if you take as Z1, and this is Jxm, then what will be the VTH value? This will be equal to Jxm divided by R1 plus Jx1 plus Jxm into the voltage V1. This is the Thevenin's voltage. And what about the Thevenin's impedance? This is equal to ZTH equals, you have to short circuit the source. So then these two resistances, impedances will appear in parallel. So you're going to get Jxm in parallel to R1 plus Jx1, which you can write as R1 plus Jx1 into Jxm divided by R1 plus J times X1 plus Xm. Okay. So these are the values, the Thevenin's values. So what will be the current value here? This implies I2 dash is equal to, from this circuit, it will be equal to, it is nothing but the current flowing in this circuit. So V Thevenin divided by Z Thevenin plus R2 dash by S plus Jx2 dash. This is in the phasor form, but we don't want the phasor form, we just want the magnitude. So you can write like this. Okay. So this will give you I2 dash magnitude is equal to VTH magnitude divided by, we can write ZTH as RTH plus JXTH. Okay, so this will become RTH plus R2 dash by S will become the real term, plus JXTH plus X2 dash will become the imaginary term. So what will be the magnitude that you are going to get? This is equal to VTH divided by root over RTH plus R2 dash by S whole square plus XTH plus X2 dash whole square. Okay, you can also write where the magnitude of VTH is equal to V1 XM divided by R1 square plus X1 plus XM whole square. Okay. Once you found out the magnitude of the current, then you can find out the air gap power. This is equal to 3 times I2 dash whole square. So this is going to be VTH whole square. Okay, so here VTH means the magnitude only, divided by RTH plus R2 dash by S whole square plus XTH plus X2 dash whole square into R2 dash by S. This is how you get the air gap power in terms of the speed. The slip here will give you an indication of the speed. Then finally, you can get the induced torque expression. T induced is equal to PG by omega S, right? So 3 VTH square R2 dash by S divided by omega S into RTH plus R2 dash by S whole square plus XTH plus X2 dash whole square. Okay. So this is the expression for induced torque in terms of the speed. So we have seen the expression of torque in terms of the speed or the slip. Okay. So this is one point. We also need the graph. Okay. The plot of T versus speed or slip. Okay. So how do we get this? For this we will use another expression. Okay. What is that expression? T is equal to K times BR B net sine delta. Don't worry, I will explain what each of these terms are. Okay. First is K. K is a parameter that is dependent on the machine construction. Okay. Dependent on machine construction. It is not dependent on the working. That means the load variations, it will not depend. Okay. So dependent on machine construction. What is BR? This is the rotor magnetic field density. And what is B net? This is the resultant magnetic field density. We have the stator as well as the rotor magnetic fields, and B net is the resultant of both these magnetic fields. That means if BR is like this and BS is like this, then B net is going to be the resultant. Okay. So resultant of stator and rotor magnetic fields. And finally, what is delta? It is the angle between B net and rotor magnetic field. So how did we get this expression? When we discussed the working of the induction machine, we saw how the torque was produced, but we did not derive a formula for it. Okay. So if we derive a formula, we will get this expression. The derivation is not important for us right now. Okay. But you need to remember this expression. T is equal to K times BR B net sine delta. Now using this expression, we will try to get the plot of torque versus the speed or the slip. Remember, we are talking about the induced torque, not about the actual output torque that is available. Okay. So what are the three factors that you have here? BR, BNet and sin delta. These three parameters, if we can get a relation with respect to speed or slip, then we can get easily the characteristic of the induced torque with respect to them, with respect to the speed and slip. Okay. So, we will go one by one. The first term we have is the rotor magnetic field. Write down rotor magnetic field. Now, the rotor magnetic field is directly proportional to the rotor current. Okay. More the current that flows, stronger will be the magnetic field that is produced by that current carrying conductor. Okay. Now, this rotor current will be dependent on the speed. How? The current is induced as a result of relative velocity between the stator RMF and rotor conductor. Okay. Now, the slip S is what gives you the indicator of relative velocity. Higher the slip, that means more is the relative velocity. Okay. Lesser the slip, that means closer the speed to the synchronous speed, so lesser the relative velocity. Therefore, we can write the rotor current increases with increasing slip, or increasing slip means decreasing speed. Okay. So, this plot will actually be something like this. If this we take as IR and the horizontal axis is speed. So, as speed increases, this IR is going to reduce and it is going to drop to 0 if the speed reaches what value? The synchronous speed. Okay. This is the speed of the rotor. Since rotor magnetic field is proportional to the rotor current, the same relation you can see with respect to the rotor magnetic field as well. So, we will write BR as well. We are talking about the magnitudes here. Next is the net magnetic field, B net. Here we will make use of the approximate equivalent circuit, that is ignoring the shunt resistance. Okay. So, now this is the magnetization current, this is Xm. Okay. Now, B net, the net magnetic field is produced because of this magnetization current, because magnetization current is the current that is taken in order to establish a magnetic field. Okay. Therefore, B net is proportional to the magnetization current. Now, we know that as speed changes, the rotor current will change. Okay. What about magnetization current? Will this change as well? Okay. So, if IR is increasing, then this current will also increase, then the drop across this will increase. So, for a particular supply voltage, as the rotor current increases, as load changes, the rotor current will increase. So, this supply current will also, it will draw more current. So, the drop across this will be increasing. So, the voltage that is available across Xm, this will reduce. So, E1 is also changing. Now, since Im, the magnetization is dependent on the voltage E1, this will also change. So, consequently, B net will also change with respect to speed, but the drop across this stator parameters are considered negligible. Okay. Drop is, voltage drop is negligible. Okay. So, you can write down voltage drop across, this is R1 JX1, R1 plus JX1 is negligible. So, even though IS, stator current, increases with increasing slip, the voltage E1 remains almost same. This implies that Im remains almost same, and finally B net remains almost same. Okay. So if you draw a plot, then you can take almost a straight line. Say this is B net and this is the speed, and this is going to be the plot of B net versus speed approximately. Okay. Next, the next term that we have is sine delta, where delta is the angle between B net and the rotor magnetic field BR. This angle will actually be equal to 90 degrees plus the power factor of the rotor circuit. Okay, that means the phase difference between the rotor voltage E2 dash and the rotor current I2 dash. Okay, so that means you can express phi r as tan inverse inductance, which is x2 dash divided by r2 dash by s, right? This is the rotor circuit. E2 dash, I2 dash, we are talking about by referring it to the primary side. R2 dash by S and X2 dash. Even if you take the actual rotor circuit, how will the actual rotor circuit be? This will be R2, SX2, this will be E2 and I2. In both cases, the angle is going to be expressed like this only. So now sine delta, how you can write? Sine 90 plus phi r, which is equal to cos phi r. Okay, and phi r, if you express in terms of x2 dash and r2 dash, then it will become s x2 dash divided by r2 dash. So you got a relationship between delta and the slip. What will happen as speed increases? As speed increases, slip will fall, and when slip will fall, what will happen to this angle phi r? It will also decrease. So this will lead to a decrease in phi r. This means that cos phi r will increase. Okay, cos phi r increases. Cos phi r is nothing but sine delta. So sine delta will also increase. So as speed increases, sine delta will increase. What will be the highest value of sine delta? It will be equal to 1. So the graph you can draw. This is sine delta. Here you have the speed. Now what will happen? As speed increases, sine delta will increase. What will be the initial value? It will be some value other than 0, because if sine delta, or this is cos phi r, if it has to be 0, then angle has to be infinite, which is not the case. You will get some finite value here. When s will be equal to 1, here the value of s is equal to 1, and here s will be equal to 0 when the speed is at synchronous speed. Okay, so there will be some finite value here. So cos of some finite value, you will get a finite value, not 0. Okay, so it will start from here and it will increase in this manner. The final value that it will reach is 1. So we have all of the 3 parameters here. First one is the magnetic field, rotor magnetic field. This will be like this. Next you have the B net, which is almost constant with respect to speed. This axis is speed. And finally we have sine delta. This is going to be like this. Okay, so if you combine all of these 3 graphs, then you're going to get the torque speed characteristics. So what will it be? From the above 3 graphs, you can see that BR is reducing with speed, whereas sine delta is increasing. Okay, initially the decrease in BR is going to be, the effect of decrease in BR is going to be lesser than the effect of increase in sine delta. So initially the torque will increase with speed. Okay, so it is going to be like this, and then slowly it will fall, and it will fall rapidly here. Okay, because at this point of time the decrease in BR will far exceed the increase in sine delta. Okay, so this is what you're going to get, the characteristic of torque versus speed. Okay, you can write down this parameters here. This is the synchronous speed and this is where the slip will be equal to 0. And here the speed will be equal to 0 and slip will be equal to 1. Now the torque slip characteristics for induction motor, they are roughly divided into 3 categories. Okay. So this is the low slip region, this is the moderate slip region and this is the high slip region. So what is happening in these 3 regions? Here you can see that the curve is almost linear. Okay. You can write down low slip region. What happens is, as the load increases, when load increases, what will happen? The speed will reduce. Okay. Now when the speed, this is the direction of decreasing speed. So when speed is decreasing, what is happening to the torque? The torque is increasing. As speed decreases, torque is increasing. Okay. So you will have increasing torque here. Here the reactance will be much less than the resistance. Now what about high slip region? In high slip region, opposite will happen. Sx2 will be much greater than R2. Now here what is happening, you can see that as load increases, the speed will anyways decrease. Now when the speed is decreasing, what is happening? The torque is also falling. Okay. Here torque will also fall. So this is not what we want. When the load is increasing, we want the torque also to be increasing according to the load, not decrease. Okay. Now the moderate slip region, this is where a maximum torque will be present. Okay. This is T max. It is also called as the breakdown or pull out torque. Okay. Maximum torque. It is also called as pull out or breakdown torque. So different textbooks use different terms. So what happens here? As the load is increasing, the torque is also increasing, but beyond a certain load, the torque will start to decrease. And the maximum load at which the torque will start decreasing, that is where we have the maximum torque, which we call as the pull out or the breakdown torque. So from this information, what can we infer? What will be the region in which we can operate the induction motor? We can operate at the low slip region where operation is almost linear. So as the load increases, the torque will almost linearly increase along with the load. So we can write motor is operated in the low slip region where operation is almost linear. So we have seen the torque speed characteristics. Often in textbooks there is some additional information. If this is the torque and this is the speed, we have seen that this is how the torque speed characteristics are going to look like. Okay, this is the synchronous speed. Now if the speed is increased beyond the synchronous speed, what will happen is it will go into the generating region. Okay, so this is the motoring region. It will work as the induction motor. So we call this as motor region from 0 to ns speed, and beyond this it is called the generating region. Now what will happen if the speed becomes negative? Negative in the sense it is moving backward with respect to the magnetic field. So in this case we call this as the braking region. Why we call it as the braking region? The induced torque will still be positive. That means it will try to reverse the rotation of this. This is a negative speed, right? But induced torque is still acting in the positive speed direction. That is why this region is called as the braking region.